Markov inequality is a very important inequality to show other concentration inequalities. So I will first show what is Markov inequality and how to show the Markov inequality, and then I will describe other concentration inequalities. So many concentration inequalities use the famous Markov inequality stated as follows. If x is non-negative, this is very important. If x is a non-negative random variable, then the probability x bigger than a is less than or equal to expectation of x over a for any positive constant a. Of course, this is useful for the case a is strictly bigger than the expectation of x. Otherwise, we have a trivial upper bound. The probability is less than or equal to 1. Because the probability cannot be bigger than 1, so that is trivial upper bound. Okay, so how to show the Markov inequality? It's very simple. So from the definition of expectation, the expectation of x is equal to integral from 0 to infinity x times the PDF times dx. Okay, and since x is a non-negative random variable, so the domain is from 0 to infinity, and all these values are non-negative as well. So when you when you ignore the range from 0 to a, so then the integral value decrease, not increase. So we have this less than or equal to sign. From integral from a to infinity, here a is strictly greater than 0, x times PDF times dx. Right. And since x range is from a to infinity, the smallest value on this range is equal to a. So when you replace x by a, we have this sign as well. So we finally have this inequality. Expectation of x is bigger than or equal to a times integral a to infinity. And this integral, by definition, is equal to the probability x is bigger than or equal to a. So now we have the Markov inequality. So the Markov inequality is tight when the probability density function concentrated at point 0 and point A. Then the probability bigger than or equal to A is exactly the same with expectation of x over A, and this value is 1 minus expectation of x over A. Right? So the Markov inequality has this sign, and the equality hold when the PDF of x have these two delta function, Dirac delta, at point 0 and at point A with constant 1 minus expectation of x over A and expectation of x over A. Then we have this equality sign. And this means if our the PDF function tail is very rapidly decreased to 0, the Markov inequality could be tight, because when when the probability very quickly converts to 0, this area, the probability density very concentrated on this area, and the probability density of this area also very concentrated here. In other words, the original PDF function roughly approximated by these two Dirac delta as this case, right? So when we have very rapid tail, the Markov inequality becomes tight as the a value move away from the expectation at the tail area. Okay, but our PDF probability density function is spread all over your domain very evenly, then the Markov inequality may be very loose. So the Markov inequality cannot give you very nice result. Maybe very unuseful concentration inequality. So to make such a concentration, such PDF property, one very common trick is MGF.